Thanks, everyone. So I'm Iain Hull. I'm a principal engineer in Workday. And if you want to contact me, feel free to reach me on email or Twitter. Also, I regularly contribute to the Workday tech blog, which you can get at this address. And I have a couple of articles to write up from this talk. Hopefully, they'll be appearing in the next couple of weeks. So, who are Workday? Basically, we're a financial and human capital management application. Basically, that means we're an ERP vendor. We're 100% in the cloud, all of our customers on one version. But I work on the Cloudmaster service. And basically, the Cloudmaster service is a data center scheduler. So the idea here is that other services need jobs executed. They send those jobs to Cloudmaster, and Cloudmaster finds resources in the data center and schedules those jobs across one of these nodes. Now, we have lots of different types of jobs or tasks that we execute, everything from printing a PDF to running payroll for maybe 200,000 employees, that kind of thing. So those sort of things have to be scaled out. The other interesting aspect to Cloudmaster is it also runs customer code. So when our customers want to integrate with something exotic, something that we don't want to write an integration for ourselves, they write their own integrations with some tools that we provide, and we execute their code in our data center. So this is a very difficult challenge for us, making sure that it's secure. Basically, this code is untrusted. So basically, our agents here are split up into different pools. So we split them into different pools based on how much memory they need, how much size, how long they run for, different scheduling concerns, different speeds, and we run them in. We run five clusters across our 5 different data centers with 4 pools in each cluster. So we're managing about 3,000 compute nodes across our data centers. Now, in the last year, the number of tasks the Cloudmaster has executed has grown very substantially. So this time last year, we were doing about 3.5 million tasks a month. And today, we're doing just over 25 million tasks a month. And this large blue line here, batch, that's a new that's people migrating processing from their services into our service. So all of this is, this big blue line is indexing a graph database. So basically, the Workday's main application is built inside a proprietary in-memory graph database. This database has to be indexed, and the indexing was killing the main database server, so it got offloaded onto us. Also, you can see the purple kind of jumped up in January, and that's when everybody in America has to print their tax returns. So everybody, in about a 1-week period, everybody presses print almost at the same time. So this talk is about the lessons that I learned when we were migrating our service off an old conventional multi-threaded stateless Java application server over to Akka and actors. So the thing is, we knew this growth was coming. As new services are migrating to our server the whole time, we have to build and continue to build and to rebuild our server. It's just part of the natural thing. I think there's a paper from Microsoft on running internet services, and basically they say every factor of 10, you have to rewrite your service again. You can't have captured all of the constraints in your first approach. You have to take new approaches and new approaches and new approaches. So we knew that the stateless Java model was never going to scale. We needed a stateful service. We needed all of our processing to be in memory. And when we were looking for the best technology to use to achieve that, we looked at Akka. And we really liked the Akka model of concurrency. We liked the fact that each actor is single-threaded, that you can't have deadlocks, that each actor itself is deterministic. It just processes one message, updates state, and processes the next message. This makes your actors easier to reason about, easier to test, and that they have a really good distribution story. So people who've come from RPC backgrounds know that RPC doesn't distribute as well as it promised, but actors basically make the you're bringing the distribution into your process. So even within your same process, you're treating it as if it's a distributed application, and that also leads to better scalability. So for my team and for Workday as a whole, I think Akka came first, and then we started learning about Scala, functional programming, and so while a lot of people don't like actors, we do use them for managing all of our state, but once inside the actor, we try to keep all of the code as functional as possible. So here are a few initial observations that we had as we started out writing our first basic actors and seeing how did they work, and kind of the basic lessons that we had. So this pattern kind of came up a lot. So you'd have some parent actor creates a child actor, and that child actor needs some configuration. So the child registers with a configuration actor, and the configuration actor sends it a snapshot of its configuration, and then periodically, as the configuration changes, it sends it to the child. Now, the thing is here that this is kind of like there's a two-way relationship here. The config actor has to know about the child, and the child has to know about the config actor. So these are really tightly coupled, and also this is like the steady state of the system, and if you have a two-way relationship with this, you have to do it with mutable data. So I played with this a lot in my first months writing actor code. How could I do this and keep my state immutable for this? And I played around with lots of things, trying to get the parent to register the child with the configuration actor and all of this. And I ran into lots of problems. But basically, the things that I learned is that you have to, first of all, your message flow has to follow a consistent path. If two actors are talking to each other, all messages have to follow the same path between those two actors. So for instance, if the snapshot was to go via the parent and the changes were to go directly, they could start arriving out of order. So whenever two actors are talking, we have to make sure they follow a consistent path. Secondly was creation. So when you're creating an actor, you should never assume that you're creating an actor from a clean state. You should always assume that it's going to fail, that basically you're recovering from failure. And nearly all of our actors now basically start up as little state machines. They start up in the idle state, and in this case, the child will start up as idle, and it'll stash all of its messages until it receives the snapshot, in which case it'll become working, and then it'll replay all of those messages. So these were the first very basic lessons in our first few months writing actor code. So now I want to talk about anti-patterns. Patterns and anti-patterns are quite a loaded term, but this talk is hopefully a lot more than a war story. Basically, when I looked at all of the problems we encountered, I've tried to think about more than what the problem is, but what's the absolute root of this problem, and how can you recognize when you have these anti-patterns, and how can you resolve them? So hopefully I've generalized these problems enough so you can apply these lessons. So first of all, everybody here who's written imperative code probably knows about the God class, especially if you're writing multi-threaded code. There's one class, it's got your mutex in it, everything, or your synchronized blocks in it, all your code ends up in this class because everything needs this mutex. So, but what's the equivalent of this for actors? What happens when our actors get too big for their boots? Well, they become movie stars. So, movie stars come in lots of shapes and sizes. Some are like Marlon Brando in his later years, and others are like Robert Downey Jr. And Robert Downey Jr. is very small, and I know that because he's the same size as me. Basically, the thing about actors is they can be big, they can be small, but they come with an entourage. And it's actually the entourage normally that is the problem, not the actor. So I'm going to have a look at an example of that now. So here's an initial actor diagram from the early versions of our application, and we can see here we have the pool actor. So the pool actor is responsible for all of these agents, and the agent actors are responsible for communication with the remote agents. And at any stage, these agents are being added and removed from the system, and the pool actor is managing that. But you'll also see over here on the right-hand side that the pool also has a queue of tasks that it has to manage, the tasks that it has yet to schedule. So the pool is managing all of the agents that are entering and leaving the system. It's assigning tasks to these agents, and it's managing the queue of all of the jobs that have yet to be processed. Now, the actor itself is quite small because most of this has been abstracted out into like utility traits and little custom data types for this actor. But all of this entourage means that there's still too much state in that actor. And this causes lots of problems. So when we have too much state, basically, first of all, it's very hard to reason about. One of the first things we discovered here was that the more state you have, the more messages or the more conversations you're actually involved in. So while you're as your state grows, you have more messages in flight. With all those messages in flight, recovery is much more difficult. So if your actor crashes, dies, comes back up, and it starts receiving 100 messages from conversations that it no longer knows anything about, that's a really difficult thing to recover from. So then also, of course, these movie star actors are really bad for concurrency. Like this is your bottleneck in Amdahl's law. So basically, the lesson here, with a movie star, you've got to break it up. The other issue actually with movie stars is they can also start to drive some very bad decisions. And we're going to see that now in my next anti-pattern. So here we have the split brain. So back to our actor diagram, we can see here that the pool, beside the pool is a state. So the pool actor is reacting to events coming in as agents are entering and leaving the system. And these events are coming in from multiple nodes in our cluster. And it was just too difficult to manage the failure cases for remote messages coming in. And really, we realized that one actor had to be responsible for all of the state changes that happened to the two different agents. And really, we should have put that into the pool actor. However, the pool actor was already a movie star. It was monstrous. We didn't want to add more state, more responsibility in there. So when we analyzed this problem, we thought that the problem was really a case of we weren't receiving a consistent stream of events into the pool actor. So we created a state actor where all modifications would go to the state actor, and it would create a consistent stream of events into the pool that the pool could respond. This is kind of it's kind of inspired by CQRS. However, the issues that we have here is that now this pool and the pool has state that's dependent on the state actor, and if this state gets out of sync, it's very difficult to reconcile. You're basically talking these things have to use like CRDTs or things like that to communicate because they can start to diverge, especially when errors happen. And when this did happen to us in production, these two started to drift. Some exception came in, entered into our system. Basically, the pool and the state one of them crashed. The state becomes out of sync, causing more failures. And basically, it ripped our service apart in production. It was quite a stressful week. Luckily, I was in Scala World, and the rest of the team had to deal with it. So basically here, the thing is, with duplicate state, you need to have a single source of truth. And this is going to come up again and again during this talk. And that synchronizing state between different actors is actually really, really hard. And basically, failure causes your state to get out of sync, which causes failures, which rips your application apart. So basically, it just starts to diverge really, really easily. So basically, the lesson here, when you have duplicate state between two actors, those actors need to be merged. Hopefully, you've already broken up your movie star, so merging these actors becomes a little easier. So the beauty about split brains is there's always two of them. So there's a different type of split brain that I came across, and when I hit it at first, I was really confused. I was really trying to find what is the lesson what's the difference between these two types of split brain? How can I know when I have one and when I have another? So in this split brain here, we have the pool has, as we said, the pool has a queue of tasks, and at some stage it's got to assign that task to an agent. And when the task is being assigned, it's no longer in the pool and it's no longer in the agent. For a split second, hopefully it arrives at the agent, and then the agent actor will send it to a physical agent, which might fail. But if it fails, the agent actor is responsible for putting it back into the pool. This seems reasonably simple at first, you know. There's a very tiny gap where the task is neither in the pool or in the agent, you know. And however, the biggest problem is that when the agent is passing it back to the pool, we don't know where it is. So if during this time somebody tries to cancel this task, the cancel comes to the pool says, oh, Agent 1 is looking after this task, I'll send the cancel to Agent 1, and Agent 1 it's already failed on Agent 1, and Agent 1 has put the task back into the pool. And the messages have just missed each other. And if we tried passing the message back up to the pool, we'd never know if it terminated. We could have that message just going around forever. So basically this is very, very difficult to reason about. And the case here is that what we're doing is we're passing a resource from one actor to another. And basically when you're doing that, or passing responsibility, you need to actually give that responsibility its own actor. And so the lessons here for passing responsibility is, it seems simple at first, but you don't always know who's in control of that responsibility at any one point in time. So when this happens, one of the sure signs that this is happening is if you have two actors and they're both trying to update the same row in the database. This means they both have responsibility for the same thing. And basically what you want to do is you want to split your actors up, so you have two actors, and then you want to bring that to three actors. So this was the piece that puzzled me the most. Was sometimes I have these split brains, and I have to take two actors and merge them into one, and other times I have a split brain and I have to create three actors. So how do I know when to apply what rule? And basically what I discovered is, if your split brain is because your two actors are sharing data or sharing state, that means that's a sign that they need to be merged together. If the two actors are passing responsibility between each other, then you need to encode that responsibility into its own actor. So the next thing, as I said, we did have some production outages, and when you notice a failure in your system and you've got to fix it as quickly as possible, this question comes up. Can you let your actors crash? So you know that an actor has crashed, my state has started to diverge, and I need to get production back up and running. What am I going to do? Like, letting it crash caused this problem. So basically at this point, the thing that we ended up having to do was the thing that caused the problem was a timeout exception, and when that hit, our actor was restarting, we ended up having to actually catch the timeout exception inside our actor. It was really, really dirty. But this happened. When this happens, it becomes really difficult to, when you know production is falling apart, can you let your actors crash? And this, we struggled with this for a while. Hopefully we've gotten past it. But basically, I'll show you the example here. So async, here our pool is passing messages to the state. So the pool is trying to launch a task, and it's going to tell the state, I want to assign this task to this agent, and the state is going to come back and say yes or no. And if something happens in this message, the reply never comes back, or if during this time, you've also got to make sure that any other messages, or any other tasks that are coming into to the pool don't get scheduled to the same agent. That agent is kind of reserved. And at this point, the thing is, can you let it crash? You know that if it crashes at this exact point, your state's going to diverge. And the thing is, when you start catching exceptions inside your actors, you're making your actors more robust. And the problem with making actors robust is you're not preventing failure, you're just preventing one instance of a failure, and the next time it fails, it'll probably fail bigger. So here, do not make your actors more robust. When you do this, this is what you found is a problem with the design of your actors. That's what has to be addressed. Now, what we've done is, or we did make the actor more robust, but we've since modified the design. And so if you have to start catching exceptions in your actors, make that like for a week or two to get over a problem, but don't leave that code in there. So there's a few lessons that we had as we after we've discovered our anti-patterns and we've resolved our issues. There's a few other lessons that we discovered. So the first thing is testing for resilience. So we have this thing in Workday now called Chaos Marmoset. It's inspired by Chaos Monkey from Netflix. And basically, Chaos Marmoset crashes actors. So basically, this is a base class for all of our actors, and we implement the unhandled method to catch certain messages, to throw exceptions, and put sleeps and delays into our actor. And now we can use this in unit testing. So at any time in our unit tests or integration tests between actors, we can inject failures in there. And we also use this for destructive system tests. So one of our test plans runs a soak test for 20 minutes, kind of processing as many jobs as it can, and during this time, as well as killing the physical agents and restarting them on the system while they're executing work, it also uses actor selection to go in, find an actor, and to either put in a sleep for 5 or 10 seconds or to make it throw random exceptions. And this way, we can see if the system is actually as robust as we think it is. And hopefully we have found that this has let us catch a lot of errors in our system and in our logic that we wouldn't have caught otherwise. So testing for failure and resilience is a very big thing. Next, as I said, we moved from writing a stateless Java application using Spring and Hibernate into Akka and being stateful. So during this time, there's code that's in, it's an iterative approach. There's code that's in both camps. Part of it is stateless, part of it is stateful, and getting the boundaries right with this is very difficult. So basically, the stateless enterprise idioms do not apply when you're writing actors. At least that's what we've found. And basically, what this means is actors have to be sovereign, have sovereignty over their state. So if an actor is writing to the database or writing to a NoSQL database or a SQL database or whatever, it needs to have sovereignty over that data. It should be the only thing writing to that table, or writing to that row, writing to the shard, or writing to the whole table. Otherwise, failure is just too hard to handle. Who's updated it? We had places where our code, an actor is responsible for an agent, an actor is responsible for a job, and a message comes in saying that this job is being cancelled or this job is about to expire, but we don't know if somebody else has updated the database at the same time. This is a disaster. We've the state that we expect the job to be in, we've got the state that the job is actually in, and we have a command to execute. And now all of a sudden, what should just be a case of applying a command to a known state turns into a matrix problem, So we're applying a command, and I think it's running, but it's being cancelled already. What should I do? It's very difficult. So the next lesson we learned a lot about atomicity. So one of the main reasons we wanted to use actors and Akka was because at the receive method of an actor is atomic. And we were really, really sick of synchronized blocks in Java and getting all our multi-threaded code wrong. So in actors, our receive method is atomic. With mutual exclusion, your scope is atomic. With actors, your state is not shared. However, with a mutex, your state is shared. It's all about sharing state. With actors, you communicate through asynchronous messages. But with mutexes, you communicate via shared mutable state. And finally, this is the most subtle thing, and the thing that nobody ever told us. It probably should have been obvious, I suppose. But basically, actors are not. You can't nest atomic operations inside each other with actors. But with mutexes, you can nest mutexes inside each other. And this is actually how you maintain consistency and acid characteristics in your applications with mutexes. So this distinction means that things that you know about imperative or functional programming, where you have access to locks, is does not apply at all when you use actors. And this kind of has big ramifications to how you design your systems. So here's a closer look at this. So here we have two actors. They're going to collaborate to do some results. So the first actor is going to send a message to the second actor. The second actor is going to send a reply, and it's going to process the result. So in the mutex case, we have the first block. Then we go into the second block, and then we come out. And the question is, what happens here? What happens in these gaps? So in the actor case, anything can happen. We're waiting for this reply. We could be processing any number of messages. Those messages could be changing our state the whole time. In the mutex case, nothing can happen. You're just blocked waiting for it. It's the same thread. So this means if you're designing a system and you're thinking in the mutex world and you're trying to send messages with actors in this world, it just doesn't work. So next, I'd like to ask, so who here thinks that banking transactions are atomic, consistent, isolated, and durable? Does anybody? So basically, we've got suspense accounts, we've got reconciliation, we've got compensating transactions. All of these things existed in accounting before computers. Accounting was never consistent. They have all of these ways of dealing with inconsistencies and non-atomic operations. So when banks are transferring money between each other, there's always a mistake, and somebody has to go back and trace through and find out. All that money ends up in a suspense account, and somebody has to go through and find out where the mistake was and execute some compensating actions. So you have to kind of let go of acid properties when you're working with actors. And the thing is, Starbucks is actually a really good example of eventual consistency. So when you go to Starbucks to order a coffee, you go up, ask for maybe espresso, Americano, say, okay, they write your name on a cup, they take your money, and that's it. They've taken your money, you've got nothing. So you have to go down to the end of the counter and wait for the barista, which is kind of a loose term in Starbucks, to make you your coffee. And sometimes you're there waiting for your Americano, and somebody else has, I don't know, skinny Frappuccino with double caramel or something like this, and they end up walking off with your Americano. And you're like, I can't drink this. So you go to the barista and you say, sorry, like this, I ordered an Americano. And they go, okay, yeah. They throw away the other coffee and they make you a fresh Americano, and you go on your way. So this is basically an asynchronous, eventually consistent transaction between you and Starbucks, or between you and two people. And so basically they're putting failure handling cases, building them into the system. And the people are actually communicating with each other when a failure happens, and they resolve it. So when you're building actor systems, you should be thinking like this. What is my failure case? How do two actors discover that there's a failure has happened, and how do they negotiate to resolve the issue? So hopefully you take something from this model. So the lessons that I picked up from this is that atomicity and consistency, these things are very different from the world that I left in enterprise Java, coming into Akka and actors, and that the actor modeling and object modeling are different. And this is kind of subtle, because people, I think, Alan Kay says that actors, that's what he kind of meant when he invented object-oriented programming. But so you kind of think that you can kind of apply these, top-down design and how you break up and assign responsibilities. You can use your object modeling skills that you've maybe learned previously, but it doesn't. They nearly line up, but in certain places, because of the way atomicity and consistency work, they don't line up cleanly enough. So this was something that caught me out a lot in the first few months working with actors. Next thing, testing for resilience and not adding robustness into your code is really, really big thing. And then finally, as you discover these things, refactor early. Don't go, I'm just going to make it work for now and I'm going to fix it later. Because from my experience, first of all, dealing with production outages is no fun. And then refactoring code when you've got a production outage is, after production outage, is really, really difficult. So with that, are there any questions?